Hello everyone, welcome to topic 8.7 pH and pKa. By the end of this you should be able to explain the relationship between the predominant form of a weak acid or base in a solution at a given pH and the pKa of the conjugate acid or the pKb of the conjugate base. We will be going over these equations here and diving into them deeper. In the generic acid-base reaction, HA plus H2O yields H3O plus A minus. We know that the equilibrium constant would be as follows. Okay, those both are the same thing depending on how you're representing the hydronium ion. If we take the negative log of this equation, the same as the P in pH, we can calculate the pKa of the solution. The lower the pKa, the stronger the acid is. So if we took the P or negative log. Or we can rearrange the equation like this below to show the Henderson-Hasselbalch equation, which we will come back to again in 8.9, but it's useful to discuss it here as well. The pH of a weak acid solution will be equal to the Ka of the acid solution when HA is equal to Ka. So we see that here, where these two, if those two are equal, this is 1, so this term drops out, and it tells us that pH is pKa, and this happens when we are at the half equivalence point. Okay. You can also see this in the Ka expression. You see that when HA is equal to A minus, then the Ka is equal to the hydrogen ion concentration. So the pKa will also be equal to the pH. Consider the reaction above. If you were to add more strong acid to the solution with equal molarity of the conjugate base and the acid, you know that the reaction will shift accordingly. Le Chatelier's principle predicts that the reaction will consume the addition of the acid, and in doing so will also consume the conjugate base, producing more of the acid. This causes the ratio to decrease. So this decreases. Okay. If the pH is less than the pKa, then we know that the ratio must be less than 1, meaning that there is a lot more of the acid than there is of the conjugate base. Okay, and so that actually is worth highlighting. Okay. The opposite is true. If the pH is greater than the pKa, then the ratio must be greater than 1, and the weak base, or the conjugate base, will be greater than the acid. So in an acid-base titration, we add an acid to a base or vice versa, and over the course of the reaction, the ratio of acid to its conjugate base changes. When all of the initial material has been consumed and the moles of the acid and base are equal, we call this the equivalence point. One way to see if a reaction has reached this equivalence point is to use an acid-base indicator that changes color at the pH of the equivalence point. We call the pH, where the color changes, the end point of the titration. Okay. Acid-base indicators are useful in determining the pH of a solution without the use of pH meters. Indicators are weak acid-base compounds or mixtures that are colored. At a specific pH value, their color will change. And this is due to changes to the structure of the indicator as the indicator gains or loses hydrogen ions. Some indicators, as you can see below, are useful at multiple pH ranges, so some of these top ones and a couple on the bottom. And it is important that you choose the correct indicator for the acid base you are interested in and investigating. If the equivalence point of an acid or a base does not fall near the color change, it will not be helpful in the determination of the titration. When choosing the correct indicator for a particular reaction, it is important to find the indicator that has a color change at the equivalence point of the acid-base neutralization. For strong acid, strong base, that is pH 7. So when you look at this, you're going to find one that changes color at pH 7. Okay? For a weak acid, strong base, that is going to be greater than 7 because the conjugate base of the weak acid is in solution and it forms the hydroxide ion at the equivalence point. And then the weak base in strong acid, the pH will be less than 7 because the conjugate acid reacts and forms the hydronium ion at the equivalence point. When deciding on an indicator, you want to be sure that the color change is completed in the steepest portion of the titration to ensure that you see the change in the color prior to titrating, to over-titrating, so too much of your titrant being added. With those titrations that have steep slopes around the equivalence point, it is a general practice to find an indicator with color change that corresponds to the pH in the middle. So middle. Indicators strongly absorb light, so you can see colors in the solution even at extremely low concentrations. In general, in order to see one color over another, there needs to be about 10 times more of one form or the other. So the acid or the acid form of the indicator or conjugate base form of the indicator. The indicator reaction can be shown as follows, where In indicates that you're using an indicator, and the H says it is the protonated form, and the In minus is the deprotonated form or conjugate base. So when we look at these, we see that the Ka for that is given, and so if you plug that into the pH equals the Henderson-Hasselbalch equation, it is given as follows. And so the tenfold rule is shown here. So that is generally a pH. So the pH for this needs to be within plus or minus 1. So the pH of the indicator needs to be within plus or minus 1 of the pKa of the acid, as shown here, or stated here. Okay. So let's practice some of this. So alizarin red S is an acid-base indicator that changes from red, pH 4, to yellow, pH 5.5. Remember that indicators are chemicals that have different colors when protonated and deprotonated. Would the protonated or deprotonated form of alizarin red S be red? Explain your reasoning. Okay, so we see that the red form is at the more acidic version. So that tells us that the protonated form, or HIN, our explanation would be at a low pH, there are lots of hydrogen ions. So the indicator should be protonated. At low pH. Okay. And thus it is red. Next, would this indicator be most effective for titration with sodium hydroxide of an acetic acid solution, which has a pKa of 4.75, or the titration of a hydrochloric acid solution? So remember that the pH of the equivalence point for strong acid-base titration is 7, and that usually we want to use an indicator that is within 1 of the pKa value. Okay, so that means, or pH value. So this one, it would mean that I would want to see an indicator with plus or minus 1 of 7. Well, The range for this indicator is not anywhere close to 7, but if we look at the acetic acid one, it is within the pH range is within 1 of the pKa value of the acetic acid solution. So it tells us that acetic acid is the correct one. And to restate it, it is because the pKa of the acetic acid it might be more like the pH range is within plus or minus 1 of the pKa. That, I think, is a better explanation, but I don't want to erase it and redo it. So the pH range is within plus or minus 1. So pH is within plus or minus 1 of the pKa. There we go. We restated it. Okay, so now the we do. The pKa of nitrous acid is 3.16. A buffer solution is made by mixing the acid and sodium nitrite. My apologies. When bromophenol blue is added to the mixture, the blue color can be observed. Which species is present in a greater amount? The protonated version or the deprotonated version. So bromophenol blue, we're going to look up here and find bromophenol blue, which is right here. And it is blue at higher pH. So I'm going to come down here. So since it is blue at higher pH, that means that it has donated its proton. So that means that the deprotonated version, or NO2, and this is because the blue indicator, or blue color, indicates more of the deprotonated species is present. Because that is a higher pH and thus less acidic. Okay, so the protons have been accepted by something. Okay, so that concludes the notes. Please complete the you do, check your work, and thank you for tuning in.